Okay, so yeah, we'll get started. Sorry for the little delay in just getting the AV set up. I'm really excited to have Nick Zentner here, but since Nick was invited by the graduate students, we're going to let Margot do the introduction today. So.
Thanks, everyone. Thanks, Is this on? Yeah, okay. Well, thanks, Akshay. Thanks, everyone. I'm really glad to introduce our speaker today, Nick Zentner. What, eat the microphone? Yeah. Can you hear me better now? Yeah. Okay. Okay, thanks. Well, I'm very excited to introduce our speaker today, Nick Zentner. As Akshay mentioned, Nick is this year's graduate student nominated colloquium speaker. And every year, the grad students in ESS get to choose one speaker for the colloquium series. It's our chance to help shape the series and to bring someone whose work interests and inspires us. We held a vote on some possible candidates, and Nick won in a landslide. So Nick obtained his master's in geology at Idaho State University, and he currently teaches geology at Central Washington University. He's won lots of awards, including the Geological Society of America Public Service Award and the Neal Medal from the Geological Association of Canada. I could go on, but he told me to keep this short. Many of you might also be familiar with Nick's award-winning PBS series, Nick on the Rocks, which has educated a broad audience about the geology of the Pacific Northwest. So I know I speak for all the grad students and the rest of our community here when I say we're delighted to have him and looking forward to his talk. Please join me in welcoming Nick Zentner.
Thank you. Thank you. Good job. Thank you, everybody. Thank you for the introduction. Thanks, grad students, for inviting me to come over. I've never spoken here at the UW, the big time, D1, R1, the whole thing. It's wonderful to be here. And props to you. It's a beautiful Thursday afternoon, 3-day weekend. You could easily be out on the road right now heading someplace, but you came to this thing. So thank you. I'm going to make this worth your while the best I can. I do need to give you a little bit more context for who I am, because I'm a weird guy, and I'm a weird guy in a weird place, and the geology I have for you today is radical stuff, and it's not my work. It's a number of geologists who I find fascinating, and they have typically been ignored, or worse, in the last few years, and I think it's worth your time. So you're here physically, and I appreciate it. The next question is, can I get you here mentally? Can I get you off the telephones right now? Is that possible? Any gadgets? Can I get them? You can tell I teach, right? I want to connect with you. I want to connect with you. I want to connect with you. So Akshay or somebody, maybe we can kill some of the lights here just to get this screen to project a little bit better, if you don't mind, and we'll just go. So the weird part about me is that I stopped at a master's degree. Thank you. Well, that's maybe too much. Maybe too much. I don't know. Maybe too much. Perfect. Right in there. Thank you, young man. Well, okay, we got. At some point, is this some sort of initiation prank you're playing on me now? All right. It's all or nothing? Okay. Look at this. All right. Johnson Hall, I'm impressed. Harold Tobin to the rescue. All right.
There's no podium control now?
It's okay. It's okay. However we want to do it. You can vote whether you want darkness or lightness. I have found ways to communicate geology to a large audience. And one way to do it is through television, and that's fine, and there's not much depth there. Nice job, Harold. That's perfect right there. Thank you. Thank you. Well done. But this is a pandemic story. We all have pandemic stories, but I'll make this quick. I started broadcasting on YouTube for the first time in my backyard. And I built a very large audience very quickly because everybody was trapped at home. And I thought when the pandemic was done, that would be the end of it. But also at the end of the pandemic, I ran out of material. All the stuff that I normally teach about, I was out. So then I suddenly started learning new things in front of God and everybody and with the learning community from people around the world, different languages, different demographics. It wasn't just a bunch of old people at home. It was scientists, it was geologists, it was plumbers, it was all walks of life, and they have continued to be loyal to what I do on YouTube. And so every winter, I pick a new topic, I go as deeply as I can, I interview people on YouTube, and I have a big enough audience now where I can pretty much get anybody I want to communicate with me in a YouTube interview style, and we learn from them directly, we read their papers, and we go. And then I put some downtown lectures together every spring and polish them up. So today's presentation is what I was doing this past winter. I'm on a couple of grants with Akshay's buddy Mike Eddy at Purdue University, and Mike and I have been collaborating for a number of years now, and so I knew nothing about the tectonics of Alaska in November, and now I know a fair amount from this deep dive this past winter. And so I've got a bunch of stuff that I want to share with you that is new to me, possibly new to you, and it's not traditional establishment geology. It's the counterculture. It's the hippie version. It's the stuff that I find fascinating, and potentially there's an impact to having us view geology in Washington in a different way. And you'll see what I mean when we get through this. So some of those downtown lectures that I just gave last month are online. This one's particularly popular, maybe because of the clickbaity title, but otherwise there's detail there, and we're going to rough out a bunch of ideas. Here's the outline for my meeting with you today. I want to start with the thrust fault basics of the Canadian Rockies. I want to get to collisional sweeps. I want to talk about westward subduction, which is a no-no for many people, but I want to explain the thinking. Ribbon continent, Stephen Johnston in Alaska, and then finally the Tintina Fault. So let's expand on this a little bit. Here's the detail that I'm going to try to put together chronologically. There are 3 collisions in the North American Cordillera with those dates. And after we do those 3 collisions, we're going to have a major strike slip fault, the Tintina Fault, break everything in half, and send the western half of those collisions 1,300 kilometers to the north. This is based on paleomagnetic data, much of which was celebrated in this building by Darrell Cowan and graduate students going back to the 70s and 80s. And then we'll do some thrust faulting in the Canadian Rockies and the Eocene. So let's start with what I think is the most conventional, non-controversial establishment thinking about the Canadian Rockies. And I was just in Calgary last week at a geology convention, and that went over like a lead balloon as we go along, but the first part was fine. So the first part is fine. Canadian Rockies, do we know some basics of the Canadian Rocky geology? I think most of us do in this room. There's thrust faults, there's shallow marine limestones and shales. The limestones are more resistant, they're ridge formers, and everything's tipped on their side. Sometimes it's folded, but it's a rather elegant scene up by Banff National Park and Yoho and Jasper and that sort of thing. So these shots from these beautiful, majestic Canadian places are the Canadian Rockies. By the way, today's title had not what I said I was going to talk about when I agreed to this a few months ago, but the Brooks Range and westward subduction is buried in this presentation. So yes, we all can celebrate beautiful places like this, that's for sure. And the conventional message for the Canadian Rockies, the Northern Rockies, is this. I think many of us know this, don't we? That the Canadian Rockies, even Glacier National Park in Montana, is built on a major detachment fault. And we're shoving a bunch of bedrock eastward on this basal thrust. That is such a different story than what's going on in Colorado and Wyoming. They're both called the Rocky Mountains, but they're built very differently from each other. I've been teaching it that way for my whole career. I've been teaching for 40 years. That story there. But what I've always taught is that these are both happening simultaneously, that this is a laramide orogeny story. And based on what number you want to pick for the beginning and the end of the laramide orogeny, you have both of these styles developing at the same time. We're going to get away from that in today's talk. We're still, though, conventional. We're not radical yet. Here's Glacier National Park in Montana, where I discovered geology as a 21-year-old, a summer kid pumping gas at Lake McDonald Lodge. Precambrian belt Purcell supergroup shoved on top of Cretaceous rocks, old on top of young. That's the Canadian Rockies story. Cross-section from a roadside geology book. Yeah, we've got Paleozoics, we've got Precambrians, we've got fold and thrust belts, we've got multiple thrust faults in here. We even have some normal faults in here. But the first major message of today is that there is no match between the upper plate and the lower plate in the Canadian Rockies. We don't have a piercing point above and below. So a major question, even today, if you ask me, is how far east did we shove this stuff on these major thrust faults in the northern Canadian Rockies? Up by Canmore, between Canmore, Banff National Park, and Calgary in Alberta. It's not the Lewis thrust, it's another thrust fault called the McConnell thrust. And this is Cambrian limestone being shoved eastward on top of Cretaceous sands. And you can put your finger right on the thrust fault. There's a lot of rock that was shoved east at least 100 kilometers, maybe up to 500 kilometers. Why? The room is quiet right now. I appreciate it. If there's an electric quietness here, I have you now. I just posted this last week, one of these field videos I did last Tuesday, I guess it was. Mount Yamnuska, near Canmore, Alberta, and asking some of these basic questions. We're heading somewhere in this talk, but we're still just talking about non-controversial messages, except we're wondering about how far are we shoving this complicated upper plate over the lower plate. This is crystalline basement that has nothing to do with everything above the thrust fault. Well, now things get interesting according to me, and maybe me only, that according to a brand new paper that came out last year, there's dates now on these uplifts, there's dates on these faults, and the northern Rockies are not being formed at the same time as the southern Rockies. And these dates of action are surprising and maybe in violent opposition to what you've been taught perhaps in this building. Northern Rockies, that major eastward thrust, where we're taking the Canadian Rockies that were in British Columbia and we're shoving them across the line into Alberta and getting closer and closer to Calgary, apparently that starts 54 million years ago. Why? And to the south, the uplifts in the Colorado, Wyoming, and southern Montana uplifts, like the Beartooth, those are starting 70 million years ago and ending precisely at the time that the northern Rockies begin getting shoved to the east. Again, all this stuff is me reporting on some interesting science papers in the last 5 to 10 years. Well, I find it fascinating that that eastward shove of the Canadian Rockies is roughly the time that North America is colliding with the large igneous province that most of us know in this room, Silesia. The Silesia large igneous province is making landfall, and I wonder if the Canadian Rockies being shoved east is tied to this major tectonic event that happens in the Pacific Northwest. Nobody seems to like this idea in print. But I don't know of anything else happening 54 million years ago offshore of us that's going to explain a major shoving eastward of the Canadian Rockies. So we'll leave it alone. But I wonder if there's a tie to the Silesia story. And if I go backwards, I think many of you might know that half of this large igneous province is no longer in our neighborhood. It's up in Alaska. The Yakutat is the other half of this Silesia large igneous province. Okay. That was a collision. Are there older collisions? One of the main things I learned this winter was a whole set of ideas that were new to me. I've been in geology a long time. I know about thrust faults. I know about hinterlands. I know about plutons. I know some have an arc magma and some have a post-collisional magma chemistry. I know about foreland basins, but I never thought about them all together as a suite. So this is my phrase, collisional suite. And I don't know if this is new to you, but this is brand new to me, and I ran with it all winter in this Alaska series. We are headed to the Brooks Range soon, and the Brooks Range in Alaska has all of these features intact, completely together, just like this index card as I've drawn with my Sharpie pens. So what is here? We have plutons in the west. We have a suture. We have other plutons to the east of the suture, but they are not arc magmas, which means subduction is not generating those magmas. At the same place that we have these slab failure magmas, we have mid-crustal metamorphic rocks that should be 20 miles down, but they suddenly are exhumed to the surface and making major mountains. We uplift the hinterland so dramatically that suddenly we have sediments being deposited both to the east and west, and we have these major thrusts. So the thrust faults are not just isolated features that I never gave much thought to. They're tied to a collisional suite, which apparently is a no-brainer if you go to the Himalayas or you go to the Alps or you go to other major collisional places around the world. But one major message today is most of these collisional suites in the lower 48 and in Canada have since been dismembered. We can only see parts of it, or they've been buried by younger lavas, or they've been invaded by younger geologic events. But some geologists are saying these collisional suites are there if you know how to find them and you know how to put these pieces of these index cards back together. So on a map, here's the same set of features that I just described, but we're now looking down from heaven. And the boundary between the old volcanic arc and the continent is here. So this collisional suite is documenting a major collision, not between two continents, but between North America's continent and an oceanic island arc offshore. Okay, so there is a geologist who has been prolific for the last 25 years. I don't know if anybody in the room is familiar with this guy's work. All of his work is on my website because I'm fascinated by his work. He is so zoomed out and thinking about Alaska to Mexico and California all the way to the Mississippi River. He's working on a scale that nobody else is. And so it's easy to discard him or ignore him because you know southern Wyoming, or you know your field area is northern Washington, and you don't know anything about Mexico. You don't know anything about Yukon. But this guy is voracious in his reading, and he's putting together narratives based on all that work. He's also a confrontational guy. And I'm usually fighting with the guy by email and phone and FaceTime, like he's just ready for battle with anybody. So that's part of the problem. He's got a chip on his shoulder because he's been, in his mind, treated poorly over the years. But I managed over the course of the winter to keep engaged with Robert Hildebrand in Tucson, Arizona, who's now 74 years old. And I kept with him the whole winter to keep him engaged and to keep magnifying what I think is very interesting work. So this is brand new paper, the basis of our meeting today. And if you can find it, great. If you can't find it, go to nickzentner.com. That's my name. You click on Alaska in the upper right-hand corner. And one of the things I love doing is taking most papers which are behind paywalls and getting them out from underneath those paywalls and make them accessible to everybody. So to give you an idea of who Bob is, I said, Bob, I'm giving talks this spring. Can you give me a couple professional headshots? So he gave me this one. He gave me that one. He's a character. But I happen to think his work is brilliant. Now, what do I know? I just teach geology in Ellensburg, Washington, in the middle of a cow pasture. So I mean, you can take my opinion, you can leave my opinion. But we're contemplating his ideas among a few others. So if we go back to the Canadian Rockies, and now we realize we have thrust faults, now we got to know what age that thrust fault is. This is not the basal thrust. This is a thrust fault that's higher in the stack, which means it must be older. And in fact, there's 3 generations, according to Hildebrand, 3 different generations of thrust faults in the Canadian Rockies that were then en masse shoved east to Calgary. So suddenly these cross-sections at a highway road sign have more meaning to me. They have more intrigue to me. It's not all happening at the same time. It's not one collisional event. There's perhaps 4 different generations of compression that we can find in these air photos and these maps and everything else. It's been worked out by generations of field geologists. Again, those same layers are not found anywhere below the detachment fault. So how far east are we moving this stuff? What scale are we talking about? How heavy? How much energy do we need to move that stuff, let alone fault and fold it? Yeah, it's complicated in cross-section. On a map, looking between Calgary in Alberta and Revelstoke in British Columbia, here's the main basal thrust that makes the Front Range of the Canadian Rockies. But I had a color scheme going this winter where green, red, and purple were the three other major collisions that had their own collisional suites. You remember those thrust faults were not acting alone. They're part of a collection of features. This is a whole new way to view major areas of geology. Not everybody loves it. In fact, most hate it. But we're continuing here today. Purple is the collision, according to Hildebrand, 124 million years ago. And over the next 20 million years, we develop collisional features post-impact. According to Hildebrand, he can find this collisional suite from red time, which is starting, the collision is happening 100 million years ago, and we go till 84 million years ago. Hildebrand says, I can find this set of features from Alaska to Mexico. In fact, even further south, Alaska to Central America. And he says, ditto for this. He's got special pet names for each of these. I just chose colors and ages. So are we able to zero in on these collisional suites? And eventually we're heading to the polarity of subduction, and that's coming next. Here's the youngest of the collisions, and instead of North America colliding with the volcanic arc, if you're asking me today, this is the large igneous province of Silesia, but we have the same features. The North Cascades is loaded with an uplifted metamorphic crystalline core, with thrust faults, the Windy Pass thrust, and so on, with some sediments. I'm not willing to just get away from this collection of collisional features, even in Washington. But that's not our focus specifically today. It is interesting that our biggest beautiful Rocky Mountains in Colorado and Wyoming are uplifting at a time when we do not have one of those collisions, according to Hildebrand. If you're an excellent student here today, the 70 to 54 is not on this list of collisions. So, honest to God, if you're asking Hildebrand, he's got 1, 2, 3, 4, 5, 6, 7, 8 separate tectonic collisions recorded in the Cordillera of North America. That's not in anybody's textbook. And you're being nice and polite here. I don't know, some of you are structural geology people and you're starting to squirm. I can see it. All right? I don't like this. I've never heard this. I reject most of this. That's fine. We can talk about it afterwards if you like. I'm reporting on this approach to find multiple generations of collisions. And the obvious question is, who are we colliding with 8 times? We're not there yet. Hildebrand is saying, if you look on land in the geology record, we have multiple collisions. Let's start with that. So yes, with putting the color scheme that I had this winter, 70 to 54 is not a collisional time, and yet that's when we're uplifting the Rockies in Colorado. We're doing a Tintina fault dance, and younger than 52, we're doing a Denali fault dance. That's coming in just a bit. But now we're getting into a radical territory where Hildebrand and others are proposing westward subduction for these 4 collisions. And then, of course, it is eastward with the arrival of Silesia. So let's go to this westward subduction concept. I think we have a mixed group here. You're all in geology or geology-adjacent disciplines, but maybe thinking about continental scale tectonics is not quite as popular as it was a generation ago. I don't know. But just in case you're unfamiliar with this concept, westward subduction, let's define what I'm saying here, because this is a big part of today's presentation. Again, not my research. I don't do any research. I just communicate other people's research. So here's the concept. If you're willing to entertain not eastward subduction, which we all know is where the oceanic plate is subducting beneath the western edge of North America, this is the opposite. This is having the North American continent long ago connected to a piece of ocean floor. So in other words, this whole thing is the North American plate. It's moving west, and our trench and our subduction is out there in the Pacific beneath an oceanic island arc. And if we have an accretionary prism, it's tied to the subduction, but the accretionary prism is way the hell out here. It's not on our margin. If we're contemplating westward subduction, we do not have stratovolcanoes on the western margin of the continent. We've got them way out here. And then a key concept with westward subduction is that you're not moving the arc and you're not moving the trench. You're moving the continent. And you're moving the continent by pulling the continent closer and closer to the arc. Slab pull. And eventually, the continent is pulled down into the oceanic trench. This is westward subduction we're looking at. And we eventually sever the connection between the ocean crust and the continent. And so we fail the slab. We break the slab after the collision. And even these major thrust faults recorded in the Rocky Mountains, according to folks who like this concept, are happening here. They're happening with the collision. It's not that we're just radically taking stuff and shoving it up onto land for some weird reason. The thought is an accretionary wedge is, and a fold and thrust belt on a major scale are all the same concept. So other cartoons to establish this idea. Continents don't like to subduct. They get pulled into the trench. I flipped this around, obviously, to make it westward subduction. And we're going to pinch this thing off. And this piece of ocean crust is going to be pinched off, and it's going to start to sink vertically into the mantle. This is an animation I have on a loop. Let's look at it a few times. I'll maybe just shut up for a second and let you watch it first in silence. I can't stay quiet. All right, so this is the North American continent that's being pulled into this trench westward. Oh, there we go. We have a massive amount of motion as we start to fail the slab, and we're lurching this accretionary wedge eastward. Again, this is North America. There's the beginning of the collision. Pull the continent down into the trench. Pull the leading edge of North America down. Start forming metamorphic rocks as we pull this stuff down. This is a tectonic model, and then we finally rocket everything back to the surface as we detach the oceanic slab. This is how we make one of those index cards that I was showing you, the collisional suites. Because before we have the continent versus arc collision, we had oceanic subduction. We had arc magmatism out there in the water before we closed the ocean basin. Okay, you've got it. So yes, that's the concept. I don't know if you love it or not. Let's just continue with the idea. Can this be found anywhere? Is this pure science fiction, or is this a real thing someplace? And the answer is, there is a real thing someplace above the Arctic Circle in Alaska that has the entire index card intact. It's a time capsule. It has not been broken. It's from 135 million years ago. And when I started the Alaska series in November, I had no interest in going to the Brooks Range. But I pretty quickly got myself interested in the Brooks Range because when I learned about the index card and the collisional suites, I was able to see the entire sequence up there. So this was a key interview. As I mentioned at the start, I emailed professional geologists. Quite often I have luck convincing them to come on camera with me. We record the conversation. I put it on my YouTube channel. And Sarah Ruskey from UC Davis was very generous with her time, 3 different times. But this one, right before Christmas of last year, she started talking about the Brooks Range story, and she described this collisional suite, and I could follow everything she was saying because I had just figured out in my mind with the Sharpie marking pens our whole suite of features. And even Sarah Ruskey, who detests westward subduction down here, loves westward subduction up with the Brooks Range. So why? Why is the Brooks Range a slam dunk for westward subduction, and yet that concept is a no-no for all of our places down to the south? Well, let's go where everybody can agree the westward subduction is the story for the Brooks Range in Alaska. Brooks Range in Alaska, gates of the Arctic. Brooks Range in Alaska. Never been. I think I'm going up there a year from this summer with Mike Eddy from Purdue University. He's newly interested in the Brooks Range because of this series that I was doing this past winter. Very satisfying to hear that report from Mike. So what is Mike interested in? Why are we going to the Brooks Range? I hope you know by now. It's going to a place that shows this collisional suite in all of its glory. Has anybody been to the Brooks Range? One guy. All right, nice. Tell me your stories after the talk. I'd love to hear about it. So here's the Dalton Highway, the Hall Road going up over Antigon Pass. This is the North Slope with all the oil in northern Alaska. Here's the Arctic Ocean and so on. And so this Brooks Range is the result of an arc-continent collision. And we're going to look at the maps and the cross-sections of the Brooks Range to see the intact story, where the volcanic arc, whatever that was, wherever that was, collided with the continent. What date? 135 million years ago. 135 million years ago. And we'll add one more thing to our index card. There's ophiolites. There's beautiful green rocks, a belt of green rocks that marks the suture between the arc and the continent. So if we go to a roadside book of Alaska by Kathy Connor, she lays it out for us. Uh-oh, we got westward subduction beneath a volcanic arc known as the Koyukuk volcanic arc. These are cartoons in a roadside book to show how the Brooks Range in Alaska was formed with westward subduction, simply meaning that we are subducting away from the North American continent. So therefore, we have subduction and we have arc magmas being generated older than 135 million years ago. Then we close the ocean, the Angiuchum Ocean. We no longer have ocean floor. We start to pull the North American continent into the trench until we finally fail that connection between the ocean floor and the continent. And this looks different, but if you squint, you can see our collisional suite. Post-collisional between 135 and 125 million years ago in Alaska. But the amazing thing is the whole suite is still there. It hasn't been cut in half. You've heard that a number of times from me now. Well, I have connections now with a number of folks from different disciplines. And this gal, Karen Siglock, is a geophysicist who now is in the south of France. She did her PhD at Princeton. And she, 20 years ago, did mantle tomography, finding pieces of ocean slab that are in the lower mantle that used to be in the Pacific Ocean basin. So Karen watches my stuff, and after Christmas she said, I saw that thing you did with Sarah Ruskey, I want to get on. I've got tomography that works beautifully with what she was saying, and the timing as well. So Karen starts talking about her mantle tomography beneath North America. Here's Juan de Fuca plate today, we all know and love. The Juan de Fuca plate continues in the subsurface using indirect mantle tomography all the way down to a depth of 1,800 kilometers depth. A continuous record of eastward subduction. Eastward subduction. Here. But what the hell's this thing? And why is it vertical? And why isn't it connected to the surface anymore? How did it get beheaded? Why did it get beheaded? Why is the top of this thing 135 million years old? In other words, Karin's work shows a steady sinking rate of these slabs in the lower mantle, 10 millimeters a year. And if the top of this thing is at 1,350 kilometers depth, and the bottom of this slab wall, as it's known, is 1,800 kilometers depth, we can take her sinking rate and equate it to time. And does this number look familiar to you? This is the collision of the Brooks Range. And she's got a slab, which today is underneath New York City, that she is saying is somehow tied to the Brooks Range in frickin' Alaska. How's that possible? The answer is North America's been drifting a hell of a lot westward in the last 135 million years. So if we go back in time and get North America way the hell off the screen to the right, suddenly we are in the North Pacific with this beheaded slab wall. So she presents this, westward subduction, just like we were drawing in the cartoons a bit ago with Elena's animation. Here's the Koyukuk volcanic arc. Here's North America coming in. This is a cartoon older than 135 million years ago because this is eventually going to be our collision. And here is this Technicolor poopy pile that's going down into the lower mantle that we're eventually going to pinch off. Scatological humor. Love it. So this thing is vertical, and it's not connected. Why? Why is it vertical, and why is it not connected? According to Karn and others who think about such things, the beheading of a slab wall is tied to a collision at the surface. And so if we have the collision, this is a tiny Atwater animation for India colliding with Asia, but we're just pretending it's North America hitting the Koyukuk Arc. I just want you to notice that that ocean floor is subducting, but then it totally detaches. There it goes. It's sinking into the lower mantle. And so the timing of when we pinch this thing off is tied to the collision itself at the surface. And analogous to a Buick hitting a moose, the Buick is North America, the moose is the Koyukuk Arc. The Buick's just going to keep motoring down the highway. So if we go back, no, I think I have it here. Yeah. So we're going to collide with the moose. The moose is just going to ride as a dead moose on our splattered front grille. As North Americans, we just keep driving, and we get this volcanic arc further and further away from the vertical place where that slab wall is today. Are you starting to see it? The Buick colliding with the moose in Alaska. In other words, North America colliding with the Koyukuk Arc. Now, Michael Eddy, who I've already mentioned a couple of times, has been a regular participant in all these programs I've been doing. And he, long ago, before the pandemic, saw what I was doing and invited me to be a public outreach person for his grants. And we've continued that for many years now. And Mike says, I have a new idea based on your recent series from the Brooks Range. I'm like, really? He's like, yeah, I've got an idea. And his idea is going to the ophiolites in the Brooks Range that are right at the suture between the arc and the continent. And he wonders if the ophiolite in the Brooks Range is all the same age. Because he says, I think we now have the geochronology tools to get good dates from ophiolites. If you're a rookie with ophiolites or this kind of geology, we're talking about a sequence of igneous rocks that are formed in a rapidly extensional oceanic basin. And it's a sequence of ultramafic mantle rocks, peridotite. You add some water, they become serpentinites. We've got some sheeted dikes, we've got some pillow basalts, we've got some deep marine sediments. So this ophiolite sequence has classically been thought of as forming in ocean basins. Green rocks today, but they were originally out there in the ocean. That's fine. In the earliest days of tectonics, an ophiolite sequence was tied to a seafloor spreading center. But we're finding these ophiolites in the upper plate, so it's hard to get these things out of the ocean and onto land. And so I've always taught about seafloor spreading centers, but Mike, in the last few months, has gotten me up to date on more modern thinking about ophiolites. There's a new thought, I guess it's not new, but it's new to me. There's a new thought that when you start subduction, when you initiate subduction, let's flip this around. When you initiate subduction of an oceanic plate, you're pulling this plate down and you're extending rapidly in the upper plate, right above where the subducting plate is starting. And so Mike's idea for the Brooks Range is, can we get a date from these ophiolites? And if we can, are the dates of the ophiolites in the Brooks Range documenting the initiation of the ocean floor subducting to make the Koyukuk Arc? That would be a pretty radical thing, an important message. Because if they're 180 million years old and it works with the base of the slab curtain that Karin Siglock has, that would be a new way to tie this mantle tomography, which most people ignore as not relevant to the surface geology. And Mike's open-minded enough to actually go for it. So yes, we say that the Koyukuk Arc is older than 135 million years old because we know the collision happens then. But Mike says, I think if we can date the ophiolites, we might be able to document the beginning of the Koyukuk Arc. Is it 180 million years? And we have ophiolites down here in Washington. If 5 years from now, Mike Eddy in the Brooks Range can say that his ophiolites are all marking an initiation of a subduction zone, then how about the Ingalls serpentinite north of my town in Ellensburg, Washington? That's 162 million years old, apparently. Same as the Josephine ophiolite in southwestern Oregon. Is there some ocean basin that's starting to subduct 162 million years old that's recorded in our green rocks? And are these green rocks found other places as well? Unfortunate color usage. All this black are the green rocks I'm talking about. So here's the ophiolite in the Brooks Range, continues down through Yukon, British Columbia, and there's plenty of ophiolites in our neighborhood as well. So this is an exciting new angle, and I'm wondering, I'm not forcing the issue now, especially since Darrell Cowan's sitting in the room, but I'm just wondering if it's possible that some of our well-known North Cascades geology is recording at least one collision with westward subduction and not eastward subduction, as many people assume. There's thrust faults, there's plutons, according to this guy Hildebrand. Some of the plutons are post-collisional, some are arc magmas. But I'm starting to see red collision for many of the geological features from San Juan Islands all the way through the North Cascades. Not in love with it, but I'm starting to warm up to the idea. Westward subduction. Okay, we've got a couple more chapters and we are done with our little session. The ribbon continent idea ties into this, and Stephen Johnston was yet another one of these geologists who has not typically been celebrated, but his important papers 25 years ago, most famously the ribbon continent of North America, and another paper called The Great Alaskan Terrain Wreck, which is a corny title, but people love it. So the idea is, Stephen's idea is that what if the Koyukuk Arc was completely linear once upon a time, as Karin Siglock is mentioning. But Karin Siglock has this slab wall that she can actually measure, and she has a length of almost 3,500 kilometers long. This is a monster slab wall in the lower mantle, the length as well as the height. So Johnston says, what if you took that original linear volcanic arc, the Koyukuk Arc, and then what if you just folded the thing up? And it can help explain some of the map patterns of the ophiolites and other features that we have in present-day Alaska. You're like, that's a dumb idea. Why would you take something super linear and have a monster length and fold the thing up? And one of the answers is there is a Z-shaped pattern on geologic maps that have been noticed by a couple of generations now. The ophiolites themselves, but other tectonic features as well. This is Alaska, even going over to Russia. Now it's in brown. From Russia through northern Alaska, the Brooks Range, folding in a big Z through southern Alaska and coming down to our neighborhood. Even on a roadside geology book from Kathy Connor, the big Z. So this series this past winter wrapped up with Stephen Johnston and Karin Siglock talking about the big Z in Alaska. And we had a roundtable discussion, as we did a couple other episodes as well, playing with these ideas of matching surface geology with mantle tomography. And I have to add again, without being unprofessional about it, these two folks were invited to a Penrose conference 2.5 years ago. They spent the whole week with a bunch of the leading Cordilleran geologists. They both wrote papers to be added to the Penrose volume, and the editors rejected both of their papers. Karin, 3 revisions and still was rejected. I just find that offensive. I'm sorry. I was watching it all happen, eating scrambled eggs. It's like, I don't get this. Why can't we have open discussions about these alternative ideas? So here are Stephen Johnston's maps. We're still in Alaska, the Brooks Range, and this major Z. And this is literally Stephen Johnston saying, man, I'm going to get online and look what train wrecks look like when they wreck. And I can see this pattern. But then you're wondering, why are we moving things north? Don't we need to move things north to get the thing to buckle to begin with? And that's the main message of the Ribbon Continent paper. Stephen Johnston saying everything's linear once upon a time from Alaska down to California. But then we start sending things north. And as we send things north, we buckle the whole thing. and there's still debate about whether we're buckling things to make the Z against the Brooks Range. Is that the stationary buttress? Or is Siberia the stationary buttress? But we need something to buckle against. And that leads us to our last part of today's talk, even though people are getting up and leaving now. I'm not going to take it personally. So we need everything west of this green line to move north to work with these ideas up in Alaska. And there are two candidates, at least, but two candidates we're talking about. The green line is the Tintina Fault. The yellow line is the Denali Fault. And we know a fair amount about the timing on both of these faults by now. And I'm not extending them further into north because we have an Alaskan orocline that kind of messes up this pattern. But let's just look at here. And here's our friend the Brooks Range today. So it's the Tintina Fault that is a new source of interest for this latest paper by Robert Hildebrand. Let's take a step back and realize that Darrell Cowan and many people in this building for many years, back in the 70s, 80s, 90s, 2000s, were focusing on a concept called Baja BC. And if you've never heard of that concept, that's a crying shame because it's tied to this university right here. It's tied also to our university, Central Washington University, because Mount Stewart is on the northern edge of our beautiful valley. Mount Stewart is where the Baja BC thing began. Also an outrageous proposal 50 years ago. This guy at Western Washington was a paleomagnetic specialist, Merle Beck. And he worked with Ted Irving in British Columbia, and he and their team, their lab, their paleomag labs, started drilling into plutons and lavas and sediments from Alaska to Mexico. And Merle still had, before he passed away a few years ago, still had the cores of Mount Stewart in one of his drawers. So the concept, and these are Darrell Cowan's, do you know Darrell Cowan sitting here? If you're a younger person, this guy's a big deal. Darrell Cowan, longtime University of Washington geology professor. These are Darrell's cartoons from 1997, 25 years after Baja BC was presented. And Darrell, during a sabbatical, put this paper together and asked for the geological community to devise some crucial tests to say yes or no for the concept that we're going to move Mount Stewart and many places west of the Baja BC Fault into place. A radical, there he is, Darrell in his backyard in 2020. This is the concept of Baja BC, that much of the rock originally in Baja, Mexico, was moved north, and much of it is in Baja, California today. Well, that didn't go over very well because the ruling paradigm still is eastward subduction of a Farallon plate. You can't do this if you have an eastward subducting plate through the whole story. And Darrell's Darrell's chronology was starting Baja BC about 85 million years ago and ending at 55 million years ago. I'm circling back to the beginning of this talk as we quit here. Doesn't feel like it, but I am. So that today, that Baja BC real estate is known as Wrangellia and the Wrangellia composite terrain. So all this crust from southern Alaska down through Yukon and British Columbia and ending down towards Mount Stewart is part of this thing that's moving north. And Wrangellia itself has a complicated history of arc magmatism, but before that, a large igneous province, some beautiful folded limestone. So we've been filming on Vancouver Island recently to document this Wrangellia story and these beautiful Quatsino limestones on top of Carmoutzen basalt. Okay, so a generation ago, the rejection of Baja BC was, you got to show me a fault. You got to show me a Baja BC fault. Otherwise, I just cannot stomach what you're telling me. And the Denali Fault, interestingly, is on the eastern margin of areas that were moved radically to the north. So did the Denali Fault somehow come down into Washington? Similar to San Andreas. People were just looking for a Baja BC fault that behaved like the San Andreas does today. We didn't expect a nice topographic surface break because the thing's not active anymore, but it was the hunt. The hunt was on for a Baja BC fault. Nobody could seem to find it to show radical amounts of translation, like more than 2,500 kilometers of motion north, according to the paleomag data. So the last part of this talk is returning to Hildebrand's new paper where he says, how about if we look east, leave looking for the Baja BC Fault, and let's go over to the Rocky Mountains and look at the Tintina Fault. Because there's been plenty of paleomag done near the Tintina Fault. And especially in Yukon, there are some lavas and some sediments that are well bedded, that are 70 million years old, and they talk about more than 1,500 kilometers of motion north since 70 million years ago. In fact, Hildebrand, in his new paper, uses 1,300 kilometers between 70 and 55. So interestingly, everything east of the Tintina shows no motion north, 0, between 70 and 54. But all these sites west of the Tintina moved 1,300 kilometers north between 70 and 54 million years ago. This ties well with the timing of the ribbon continent folding up. And so the concept that's radical for many is that the Tintina Fault extends underneath the Canadian Rockies, dashed, and continues down into the lower 48, dashed. Everybody hates that. But the paleomag, consistently west of this dashed green line, west of the Tintina Fault, shows 1,300 kilometers, plus or minus major errors, to the north. And so instead of looking for a Baja BC Fault here, Hildebrand in his new paper says it's not just the western sliver of North America, it's everything west of this green line that's moving 1,300 kilometers north. And suddenly, the Canadian Rockies being formed in Nevada originally and then moved up to Alberta and British Columbia is not such a radical thought. Even though these maps are radical, you got to be shitting me. You're going to take the Tintina and have it come down through the Snake River Plain? Give me a break. Open your mind, man. Open your mind. Tintina Fault coming all the way down to the Texas lineament in Southern California. The final piece of today is the evidence not just of the paleomag, but back to the collisional suite. If you remember our purple 124 million year old collision, we have all these features indicating a collision 124 million years ago. Here's one of the most key diagrams of today. Hildebrand proposes, if I go back, once upon a time this was an intact collisional suite card formed between 124 and 105, and it stayed intact until 70 million years ago. And then what happened? The Tintina Fault, the green line, shows up 70 million years ago. It takes the original half of the index card that was down here in Nevada, moves it north. And you're like, why is this thing being moved north? Well, it's not just this thing. It's everything. It's everything west of the line moving 1,300 kilometers to the north. So what's in Alaska was down in Washington originally. What's in Washington was down in Mexico originally, Baja, BC. And this collisional suite, half in British Columbia and the other portion down in, oh, they're wrapping me up now, in Utah and Colorado, that's Hildebrand's main message. We're back to that. It's fine. And so the idea that the eastward shoving that we started with is happening late tells us, according to Hildebrand, that this Tintina Fault, which actually sent the Canadian Rockies north, then gets concealed by this youngest chapter of Silesia-related eastward shoving. So this new lecture online goes through that. And here on the chalkboard, I'm showing the intact purple card, then it gets moved north, and then the last chapter is shoving the Canadian Rockies over the very fault that sent it north. So we're still on speaking terms here with Robert Hildebrand. And this Canadian Rockies story ties in with so many other major narratives that were discussed this past winter. So these days of always eastward subduction, always simple eastward subduction, since the days of breaking up Pangaea, This may be true for South America, but I just cannot see how that simple eastward subduction story for 180 million years can still be taught and still be published for our latitudes, based on the mantle tomography, all the strike-slip motion that we have today. Instead, using Karn Siglock's work with Mitch Mahalanik in British Columbia, they view a double subduction story on both sides of something they call the Orcus Plate. And this whole kit and caboodle is going to be invaded by a westward drifting North American plate, and then Baja, BC is going to be put right into that. So we're going to go to that to finish this animation twice, and we are done. This is from the mantle tomography. That's nothing to do with the index cards. This has nothing to do with the Brooks range. This is just coming from the position of these ocean slabs that are vertical in the lower mantle. 70 million years ago, send everything north. That's from 6 years ago. Let's zoom in and do the same thing. The purple is the Canadian Rockies, essentially. The orange is Wrangellia. The red is the Koyukuk Arc. And there's a bit of timing problems with Alaska and the Brooks Range with this, but I just want you to notice 70, move it north. I find it hard to believe that's a coincidence, that this paleomag on the surface and this mantle tomography are both pointing to the same conclusion of massive northward motion of much of western North America starting 70 million years ago. So it wasn't my intention originally when I started this series, but I ended up celebrating these three geologists who have not been welcomed with open arms among North American Cordilleran geologists. That was my attempt to put this together. This is my attempt to summarize, and I thank you for your attention this afternoon. Thank you. Thank you. We can do question and answer in the dark. We cannot do question and answer at all. Fluorescent 3.
We can do some questions. Anyone?
If you've had enough, you've had enough, and thank you for coming. Don't be shy. But yeah, we can do a few if you like.
Is there any kind of fossil evidence that supports this whole story?
Is there any fossil? You can hear the questions. What's his name? Peter Ward had some angles to play with, I'm not going to have the details. Daryl? The Nanaimo group has been translated to the north up by British Columbia and in the Salish Sea. Some nautiloids and some ammonoids from Peter Ward that he's published on a little bit, but that's an angle that I wasn't able to follow. I think there's surprising palm fronds in the Nanaimo group that are too old for the Paleocene-Eocene thermal maximum, and so they may help get things further south originally. There may be a few other stray thoughts, but it's not a major collection of fossils that help support this work, at least that I haven't been able to find. Anybody else want to ask anything?
Thanks, Nick. I haven't followed, any of this part of this controversy, but you kind of portray this as three mavericks and everybody else just says nah.
Right.
So what's the nature of the objection? Why the nah? What's the counter argument?
Thank you. Well, I asked each of those folks on camera if they can put it in their own words, at least for their most recent papers that were not allowed to be published. And I took Karin's preprint and just posted that with the third revision. I'm trying to be professional here. It doesn't match the known local geology. These are assumptions that cannot be proven about a sinking rate, let's say, with the mantle tomography. These are messages that are nothing new. This is from 20 years ago. But I reject all of those statements. But it's different than the Baja BC thing, where we just can't find a fault, which is not really the right way to frame a criticism anyway, in my opinion. But I'll maybe say it this way. I think for 50 years, the paleomagnetic data set has been criticized by criticizing the method, mostly by people who are not in geophysics or trained in a paleomagnetic lab. And so they don't like the message, and so they're just saying they must be doing something wrong in those labs. And interestingly, the same approach has been done with the geophysics and the mantle tomography. They must be doing something wrong with these assumptions, and like they're finding these things in the lower mantle. I'm not sure they're finding what they think they're finding. So it's interesting that they're attacking the process as opposed to the data sets themselves. And admittedly, it's very difficult. Who can sit here and say, I know everything about paleomag and everything about mantle tomography and everything about field geology from Alaska to Mexico? Nobody can do that. Hildebrand says he can, but everybody else can't do that. So it's difficult to find enough people who are willing to think on that scale to at least entertain these thoughts. And then what is the next generation supposed to do? I don't know. But I'm just trying to amplify some of these things, which I find fascinating. I think it's ironic that, I can't believe it's all a coincidence, I guess is my point. Many of these different kinds of work, all pointing to some rather similar conclusions. It's fun to think about. And it answers some questions and opens up some others as well.
Thank you for the great talk.
Thank you.
I'm curious if there's a piece of field evidence or some new geophysical technique that you would almost be a low-hanging fruit or something to help prove this theory or another. Does it lie in the ophiolites, like you mentioned, or kind of what are you seeking or pushing as the next thing to do?
Thanks. I'm not sure I'm the person for that, but I am excited about the ophiolite thing. Many of us are drawn to simple messages, at least I am for my brain. So if these ophiolites are truly tied to subduction initiation, and if we can go through that whole Z in Alaska, and it's all 180 million years ago, for instance, that would be a dream. But if that was true, then we clearly need to lean into tectonic models that show all that stuff forming in the same subduction zone. And then if we can go to other ophiolite belts as well. I'm tooting Mike Eddy's horn too much probably today. He'd probably be embarrassed. But we have done a number of these interviews. Apparently all these ophiolites on the other side of the world, in Cyprus, and I don't even know all the locations, they all have the same age. They're all tied to the same subduction initiation story. So I find this wild that something this worldwide with a simple technique that can be applied to large areas, that might be a leap forward. It might be a big deal if those dates are as simple as they might be. That's one example, but otherwise, I'm just hoping more people are going to work on this scale. It just doesn't seem like most are willing, professionally or otherwise. It's just not, it's too risky politically. I don't know, like, it's safer to stick with one little field area and publish on it for 35 years and call it a career, but it doesn't sound like a lot of fun to me.
We'll take one more question.
One more, that sounds good. It's a nice afternoon. You guys got to get outside.
Thank you. So Harold asked my question, so I will follow up on that with, you said one of the big oppositions, aside from just, this is what people have been saying for so long, is that it doesn't match like local field geology.
Yeah.
And so I'm curious, like you said, no one knows the whole stretch everywhere, but in diving into this, have you seen any cases of someone saying, we thought we understood this local geology, but actually this weird story might help explain some standing questions? Right.
Thank you. I'll choose to answer it this way. it shows how pathetic the situation is, actually. So somebody will say, yeah, let's do a recorded interview on whatever topic it is related to these things I'm talking about. And they give their public thing. And then they say, okay, are we done? We turn the camera off? Are you done recording, right? And they go, I think it's actually this other thing. I think it's, you know. And so I'm just unfamiliar with that world of reputation and funding sources and other things. But I've seen enough of that as kind of this neutral, trusted person. Like, oh, no, I think it's, come on, man. What are we doing? And it's not just early career people. So it's societal, it's psychology and sociology, way more than most of us are willing to admit. So I'm trying to be optimistic, and it is fun to find narratives like this. Could all be wrong, but I think it's intellectually stimulating to try to play with some of these ideas, and I hope it continues down the road. Thanks for coming this afternoon. I do appreciate it. Thank you.